Welcome to the video on vector equations of planes. So for the vector equation of a plane, we have this right here, where r equals a plus gamma b plus mu c. So b and c are non-parallel vectors within the plane. So in 3D, you'd have your x, y, and z axes. A is a position vector, and then B and C are two vectors along your plane. So if your plane looked something like this, if you had points here, and then your plane extended forever, so it would be like that, and then it goes into all the directions. A would be a position vector showing one point on the plane. So A could be a vector from here to any point along the plane. And then B and C are vectors on the plane. So they could be like these on the plane. Our equation using a normal vector is r dot n equals a dot n. And that's where n is a normal vector to the plane, and a is the position vector of a point on the plane. And r would be your x, y, and z vector. In Cartesian form, you have ax plus by plus cz equals d. So we'll do some practice with these equations in our practice problems. Here we have our first IB practice question. It says a plane contains the point 1, 3, 2 and has the normal vector 2, negative 1, 6. Write the equation of the plane in Cartesian form. Is the point 2, 6, 5 on the plane? So there's two things we need to do. We need to write the equation, and it has to be in Cartesian form. And we also need to find if the point is on the plane. So we have a position. So A is 1, 3, 2. So this is going to be our position vector. And then we have our normal vector, which equals 2, negative 1, 6. So we'll use our equation that uses the normal vector. So r dot n should equal a dot n. So r dot 2, negative 1, 6 should equal 1, 3, 2 dot 2, negative 1, 6. So our first part, we'll split r to be our x, y, and z. So we have x, y, z dot 2, negative 1, 6 equals 1, 3, 2 dot 2, negative 1, 6. So then we'd have 2x minus y plus 6z equals 1 times 2 is 2 plus 3 times negative 1 is negative 3 plus 2 times 6, which is 12, so plus 12. So 2x minus y plus 6z equals 2 minus 3 plus 12, which is 11. So this is our equation in Cartesian form. And now we want to see if the point 2, 6, 5 is on the plane. So we'll plug in 2, 6, and 5. So for x, we'll plug in 2 minus y, which is 6, plus 6 times z, which is 5, and we'll see if that's 11. So we have 4 minus 6 plus 30 equals 11. 4 minus 6 is negative 2 plus 30 is 28. 28 does not equal 11, so the point 2, 6, 5 is not on the plane. So another thing to note is in Cartesian form, we have 2, negative 1, 6. And that was our normal vector. So our normal vector is built into this, and then we could have plugged in our point to solve for what d would be. So both ways work. Now we have our second IB practice question. It says find the normal vectors for the following planes, then find the angle between the planes. So our components of the normal vector are going to be our x, y, and z coefficients in our Cartesian form. So here, our normal vector would be 3, 2, 1. And here, our normal vector would be 1, negative 4, 3. So these are our normal vectors. Now we need to find the angle between the planes. To do this, we could find our angle between our normal vectors. So that would be v dot w equals the magnitude of v times the magnitude of w times the cosine of theta. So v would be 3, 2, 1 dot w, 1, negative 4, 3 equals our magnitude of v, which is the square root of each component squared and added together, times the square root of 1 squared plus negative 4 squared plus 3 squared, and then times the cosine of theta. So we have 3 times 1, which is 3, plus 2 times negative 4, which is negative 8, plus 1 times 3, which is 3, equals our square root of 3 squared, which is 9, plus 2 squared, which is 4, plus 1 squared, which is 1, times the square root of 1 squared, which is 1, plus negative 4 squared, which is 16, plus 3 squared, which is 9, times the cosine of theta. 3 minus 8 plus 3 is negative 2, and that has to equal the square root of 9 plus 4 plus 1, which is 14, times the square root of 1 plus 16 plus 9, which is 26, times our cosine of theta. We'll divide by the square root of 14 times 26, which is the square root of 364. So divided by the square root of 364, those will cancel. So then we get that cosine of theta equals negative 2 over the square root of 364. 364 is 4 times 91, so we can pull a 2 out of the radical. So this is going to be negative 2 over 2 root 91, which then we simplify to negative 1 over the square root of 91. So cosine of theta equals negative 1 over the square root of 91, which we can rationalize by multiplying the square root of 91 over the square root of 91. So the cosine of theta equals negative root 91 over 91. So theta equals the inverse cosine of negative root 91 over 91. So that's our final answer because this is a no calculator problem. So that's as simple as we can get it. If it had been a calculator problem, you could plug that in and find that theta is approximately 96 degrees. So there's your solution to that problem. So in summary, our vector equation of a plane is this equation here where B and C are non-parallel vectors within the plane. And then using the normal vector, you would use this equation where n is normal to the plane and a is the position vector of a point on the plane. And finally, this is our Cartesian form for a plane, where A, B, and C would be your normal vector. That's all for this video. Thank you for watching.